Section 6.2, Determining Volumes by Slicing. In this section, we're going to look at how we can use integration to help us find the volume of a solid. The first method to finding the volume of a solid is to try to use what we call cross-sections of that solid. The cross-section of a solid is the intersection of a plane with the solid. So for example, in 3 dimensions, we can see here on the left this half cylinder, and we can see the plane that is intersecting that solid. The cross-section would be the intersection of that plane and that cylinder, which here would be a semicircle. Now, if the solid has cross-sections that are the same shape, but maybe different proportions, we'll see that we'll be able to find the volume of our solid using integration. Now, how can we use integration to help us find the volume of a solid through this slicing method? We're going to let A of x be the area of a cross-section of a solid S. And notice how the area is going to depend on the value of x. So for example, if I look at the solid here on the right, that would be one cross-section there in yellow, and that would be another cross-section there in orange. Each cross-section has the same shape, but does have a different area. But similar to the idea of finding the area using integration, we could estimate the volume of those cross-sections, assuming that throughout the partition that it has the same area A of x. Thanks to the Riemann sum, we can find the volume of S bounded between the planes of x equals A and x equals B by integrating the area function A of x over the interval A to B. In other words, the volume of our solid would be equal to the integral from A to B of A of x dx. Now, this process can be a little tricky at first because you do have to think in 3 dimensions, and drawing in 3 dimensions can be a little tricky. But here's a rough procedure that we will use. First, you want to examine the solid and determine the shape of the cross-sections. And it's often helpful to draw a picture if one is not provided for us. You definitely want to make sure you have visual aid, since this is a very geometric process. From there, you want to determine a formula for the area of the cross-section, and this formula will depend on x. Finally, integrate that area formula over the appropriate interval in order to obtain the volume of that solid. In this example, we're going to use the slicing method we discussed on the previous slide to find the volume of a right circular cone with a height of 5 and a radius of 9 using integration. Now, typically when we draw cones, we tend to orient them vertically. However, since we're trying to use the slicing method, we're going to orient our cone so that way the point is located in the origin and the x-axis runs through the center of our cone, like so. From here, we can start to try to analyze the cross-sections of this cone and find the area of each cross-section. Keep in mind that the problem tells us the height of the cone, which here will be horizontal, is 5 units, while the radius is 9 units. Now, what would each cross-section of our cone look like? Well, each cross-section would just be a circle. But how would we find the area of each cross-section? Since we know our cross-section is a circle, the area of a circle can be calculated with pi r squared. So we need to find the radius of our cross-section. The way we can do this is very similar to what we have done in related rates problems. Our cross-section creates a cone within the cone. The height of this new cone is going to be x units. Since we made our tip the origin, the height would have to be x units away from the origin. And the radius, we're going to call for now r. As we saw before in the related rates problems, the height of the cones and the radius of the cones are perpendicular, and they can create a right triangle with the lateral height. These two triangles will be similar triangles, which means they'll be proportional to each other. Since we're concerned with finding the radius, we're going to put the radius on top of the height. So r over x for the cross-section cone is going to be equal the radius to the height of our original cone. And if we solve for r by multiplying by x, we get r equals 9/5 x, which means the area of any cross-section, which is going to be a of x, is going to be pi times 9/5 x squared, which is 81 over 25 pi x squared. Now that we have our area of the cross-section, our volume is going to be the integral of our area function that we just found. As for the bounds, because of the way we drew our cone, we can see that the lower bound will be 0, while the upper bound will be the height of our cone, which is 5. The antiderivative of 81 over 25 pi x squared is 27 over 25 pi x cubed. Plug in our bounds, and we get that the volume is 135 pi. Now, you might be thinking to yourself that there's already a formula to calculate the volume of a cone. B equals 1/3 pi r squared h. If we do use this formula, we do also get 135 pi. So this example isn't just to overcomplicate the process of finding the volume of a cone, but to show that this process is still consistent with what we already know from classic geometry. If our solid was a little bit more irregularly shaped, which we'll see later, this process of integration becomes more necessary. One of the most common ways of forming a solid is to take a region in the xy plane and revolving it around the line. We call these solids of revolution. So a solid of revolution is a solid that results from revolving a region in a plane around a line in that plane. To demonstrate the process, suppose we have this region here and the xy plane that we see on the left. We can begin to revolve it around the x-axis. And as we revolve it around the x-axis, we wind up with a solid. What's interesting about this solid is that the cross sections are all circles. The radius of the circle would correspond, in this case, to the function value, since we're revolving around the x-axis. Cones are examples of solids of revolution. Our region would be a triangle, and the function would be a straight line that passed through the origin. So we can adopt a similar method to what we saw in the cone problem to help us find the volume of these solids of revolution. Now, depending on the region that we're rotating, we have a few different methods to calculate the volume of the solid of revolution. The first method we're going to look at is referred to as the disk method. We're going to let f of x be continuous and non-negative, and we're going to define R to be the region bounded above by the graph of f of x and below by the x-axis, and on the left by the lines x equals a, and to the right by the line x equals b. Then the volume of the solid of revolution formed by revolving R around the x-axis is given by v equals the integral from a to b of pi times f of x squared. The reason for this formula is, as we saw in the previous slide, our cross sections are circles. The area of a circle is pi r squared, and as we saw in the previous slide, the radius would be the function value, since the x-axis is the center and f of x would form the outside of the circle. So our area function would be pi times f of x squared. So as an example, we're going to find the volume of a solid obtained by rotating the region enclosed by y equals the cube root of x. So just like in past examples, we'll start by sketching our region. We'll start by graphing our vertical lines. First is x equals 1, then x equals 8. As for the cube root graph, let's see where it will intersect the vertical lines x equals 1 and x equals 8. When x equals 1, y would be the cube root of 1, which is 1. So we'll plot the point 1, 1. When x equals 8, y is 2. So another point would be the point 8, 2. The cube root graph does look a lot like a sideways x cubed graph, which looks close to this. As for the region, it will be the region bounded between the two vertical lines, our x cubed graph and the x-axis, which will be this region here. This gives us an idea of how to set up the integral. Because we're finding the volume using this method, and we're revolving around the x-axis, our volume is going to be equal to the integral. As for our bounds, just like with our area between curves problem, our bounds would correspond to the largest and smallest x values within our region. Our smallest is 1, our largest is 8. So we'll be integrating over the interval 1 to 8. As for our integrand, according to our disk method formula, it's going to be pi times our function squared. So our integrand would be pi times the cube root of x squared, which is the same as pi x to the 2/3. Now we can find our antiderivative, which would be 3 pi x to the 5/3 all over 5, plug in our bounds, and subtract, and we get that the volume of the solid will be 93 pi over 5. Next, we're going to find the volume of the solid obtained by rotating the region enclosed by y equals 6x minus 3x squared and y equals 0 about the x-axis. One thing to note is that the line y equals 0 is the equation that represents the x-axis. So because we're revolving around the x-axis and one of the bounds of our region is the x-axis, that tells us we are using the disk method. Now we'll sketch a graph of our 6x minus 3x squared equation to get an idea of the region. We'll start by finding the x-intercepts, since that is where our y equals 6x minus 3x squared would intersect the line y equals 0. So we're going to solve the equation 6x minus 3x squared equals 0. Since this is quadratic, we will factor the equation, and we get 3x times 2 minus x equals 0, which means x equals 0 or 2. So we'll plot our two x-intercepts, and since we only have the one parabola and we know it's upside down, we know the vertex would be in the middle of the x-intercepts, we can just quickly sketch our curve like so. Remember, when we are sketching the region, we're just trying to get an idea of what the region looks like. We don't need a perfect drawing. And our region would be the portion between our parabola and x-axis, as we see here in orange. Now that we have our region drawn, we have an idea of how to set up our integral. The volume is going to be equal to the integral. As for the bounds, our lower bound will be 0, our upper bound will be 2, and because we're revolving this region over the x-axis, our integrand would be pi times 6x minus 3x squared, quantity squared. The problem with this integral is that we can't use a substitution. If we make our u 6x minus 3x squared, our du would be 6 minus 6x, which we don't see in the integrand. So instead what we'll do is we'll expand out the square. When we expand our 6x minus 3x squared, our integrand will become pi times the quantity of 36x squared minus 36x cubed plus 94x to the 4th. Now from there, we can apply our power rule. Then we can plug in our bounds and then subtract the results, and we get that the volume of our solid of revolution is 48 over 5 pi. Oftentimes, the region that we're rotating to form our solid may not be bounded below by the x-axis, and instead bounded below by another function. When our function is bounded below by another function instead of the x-axis, we'll use what we'll call the washer method. We're going to let f of x and g of x be continuous non-negative functions such that f of x is greater than or equal to g of x over the interval ab. We're going to let R be the region bounded above by f of x, below by the graph of g of x, and on the left by the line x equals a, and on the right by the line x equals b. Then the volume of the solid formed by revolving r around the x-axis is v equals the integral from a to b of pi times the quantity of f of x squared minus g of x squared. To help us demonstrate why this is true, let's take a look at the example below, where we're finding the volume of a solid obtained by rotating the region enclosed by the lines y equals 3x plus 1, y equals negative 3x plus 7, and x equals 2 about the x-axis. We'll start by sketching our region. X equals 2 is a vertical line, which we'll sketch in blue. Next, we'll find the point of intersection between our two lines, y equals 3x plus 1 and y equals negative 3x plus 7. We'll do that by setting 3x plus 1 and negative 3x plus 7 equal to each other, and then we can solve the equation, and we get that x equals 1. To figure out the y coordinate, we can take x equals 1, plug it into either the y equals 3x plus 1 or the negative 3x plus 7, and whichever one you pick, we're going to get y equals 4. So our two lines are going to intersect at the point 1, 4. Now we'll figure out where y equals 3x plus 1 intersects the vertical line x equals 2. Since x equals 2, we can just plug 2 into the equation, and we get the y value is 7. Since y equals 3x plus 1 is a straight line, we can connect the dots. We'll do the same thing with y equals negative 3x plus 7, plug in x equals 2 to see where that line would intersect with the line x equals 2, and we get 1 as the y component. Now we have 2 points. We can connect them to make a straight line. As for the region that we're rotating, that'll be the region bounded by all 3 lines, which would be that triangle there. Now that we have this formula, let's go back to the explanation of why our formula for the washer method is the way that it is. Suppose that yellow portion represents part of the cross-section that is being formed when we revolve our region around the x-axis. This would create a washer, which is a hollowed out circle. The way we calculate the area of a washer is we would find the area of the big circle without a hole cut into it, which let's call that pi r squared. And we would subtract off the area of the little circle, which let's call pi little r squared. In this scenario, when we're looking at the general formula, since f of x is bigger than g of x, then f of x is going to be the radius of the outer circle of the washer. So in our formula, big R would be equal to f of x, and g of x, being the smaller of the two, would be the radius of the smaller circle. And that's how we get the integrand that we see. And then from there, factor out the pi, since that would be a common factor of the two terms. So now we've gone over the formula. Let's apply the formula to find the volume of this solid of rotation. Our volume would be the integral from here, it would be 1 to 2, 1 being the smallest x value of our region, 2 being the largest. And our integrand would be pi times the equation that forms the upper bound of our region, which is 3x plus 1 squared, minus the equation that's forming the lower bound of our region, which is negative 3x plus 7 squared. Now from there, we will simplify our integrand, and when we expand the squares and collect like terms, we get 48x minus 48. Find our antiderivative, which would be pi times 24x squared minus 48x. Plug in our bounds and subtract the results, and we get that the volume of our solid of rotation is 24 pi.